Picture we have a teeter-totter. And so let's say that there's two people. One has mass M1, the other has mass M2. And for starters, I'm going to put the fulcrum somewhat in the middle of the teeter-totter. So since both of the people sitting on the teeter-totter have mass, it means that there's going to be a gravitational force on both of them. And so the gravitational force is what can supply a rotation of this teeter-totter. If you can imagine, right now the red line is level, but you can probably imagine if the force on one side or the other is greater, you're going to start to see it tilt. And so what we are interested in here is the familiar concept of force, but now force being applied to make an object rotate. And so both the force of gravity on the first person on the left and the force of gravity of the second person on the right are potentially going to make this teeter-totter rotate. So for simplicity, let's just focus on one side for the time being. So I'm going to go ahead and clear out the left side. And let's just focus on the right for a moment. Before we return to the two people on the teeter-totter, let's just talk generally about if you have some mass M, and let's say there's just some arbitrary force, like say going in this direction. So that force is acting at a distance r away from the center, or in other words, the axis of rotation, which is where I have that fulcrum right now. You see how I can also express the radius from the center of the axis of rotation to where the force is applied. I can express that as a vector, and that is the vector r with the arrow on it to also show that it has both a magnitude, which is the radius, but it also has a direction. It's pointing to the right. And with vectors, you can slide vectors as long as you preserve their length and their direction. You can slide them all over space so that it's more convenient for you to think about the angles it makes with objects of interest. And so you see what I did there? I just took the radius. Sometimes this is called the lever arm. This plays a role in the term called leverage, which I hope will make more sense in a moment. But I can just slide that vector so that I can think of it making some angle theta with the force that's being applied. And just to simplify things here, I'm going to erase so that we don't get too messy. So I hope you're following that for some mass M, there's some lever arm, which is a vector r that has both magnitude and direction, where the magnitude is the distance from the center of rotation, i.e. the axis of rotation. And it's projecting radially, in this case, out to the right. And then there's some force F. And the question now is, how much of that force F actually gets this object to rotate? Because you can imagine if I decompose this vector, so let's call that Fx, and let's call this component of it Fy. I hope you can see that the Fx, i.e. the horizontal component, that's not going to cause any rotation. None at all. It's the y component of the force that would actually get the red line, if you will, to start swinging in a counterclockwise direction. Fx would just stretch it. And so it's this component of the force that actually supplies a torque. Now, technically, we would say that the torque is equal to, and you're not obligated to know this, but it would be the cross product, which is to say whatever the force is crossed with whatever the lever arm is. And those are both vectors. So that's like a vector multiplication, but you're not obligated to know vector calculus. And so I want to show you another way of thinking about this. And so going back to the force and how it has both an x component and a y component, and how the x component is only going to stretch and the y component is going to actually supply rotation. So you see that blue angle theta. So you've had some experience decomposing vectors where you would find that the x component of the force would be equal to the magnitude of the total force multiplied by the cosine of theta. And similarly, if I want to figure out the magnitude in the y direction, I have to start with the overall magnitude, and then I have to have a sine theta term. And so this term right here, that is the part of the force F that's actually going to supply rotation. And so torque can be written as the magnitude of the overall force times the sine of the angle between the force and the lever arm. And so that's one way of writing torque. I'm going to show you another way in a moment. A couple things real quick. So what's important here is that we also have to consider the lever arm. So we have the component of the force that's acting in the direction that actually supplies rotation. But then we also have to think about what distance r is that particular force acting vis-a-vis the axis of rotation. So I'm just going to rewrite this as the magnitude of F, and then we're going to think of the magnitude of the lever arm. So just the distance from the axis of rotation to the mass, and then the sine of the angle between the two. So obviously force matters. The orientation of the force matters. If you can imagine, the greater theta gets. So imagine that theta was 90 degrees. So then you would have the force completely perpendicular to the lever arm. So all of the force is acting in a direction that's going to rotate the object. And so if you think about sine 90 is 1, which is the maximum value sine can be. So that's when you would have the maximum torque. So the orientation between the lever arm and the force matters. Now, similarly, imagine that theta was 0. So in that case, the force would be completely in the direction of the lever arm. And so it wouldn't be doing any rotating at all. And what's the sine of 0? The sine of 0 is going to be 0. So the orientation matters, but also what matters is the distance from the force being applied to the axis of rotation. And so going back to the fulcrum, let's say that instead my fulcrum was right here. So now you could probably imagine, right? It's not as far away from the mass as it was here. And so this term right here, the lever arm, you can imagine as that term gets larger and larger, for the same amount of force being applied and the same angle between the force and lever arm, as that R gets larger and larger, you're getting more and more torque for the force that's being applied, which is to say that you're getting more leverage. That's what it means to have more leverage, is that for the same amount of torque being applied at the same angle of application, the larger and larger the lever arm is, the more and more leverage you're going to get. So for the same mass starting to rotate, this fulcrum gives you greater leverage than this fulcrum. So that's the idea of leverage. So one more time, when you're thinking about torque, you have to think about three things. You have to think about, okay, first of all, what is the magnitude and direction of force being applied? Then you have to think about what component of that force actually is going to supply rotation. And then you have to think about how far away is that force acting from the axis of rotation. So let's go back to our teeter-totter. You have M1 and M2. And again, let's put the fulcrum towards the center. So essentially, you're going to have two different torques acting on the teeter-totter. You're going to have a force here due to gravity on the person of mass 1, and so that's M1G. And then you're also going to have the force of gravity on the second person. And so there's two different lever arms here. So you have R1 and you have R2, and you can just simply imagine, right? You know, R1 is going to have a magnitude from the fulcrum out to the first person, and R2 is going to have a magnitude from the fulcrum out to the second person. And then I just moved the vectors out so it can be more clear, because again, you can, as long as you preserve the magnitude and direction of a vector, you can move it anywhere in space. I want to make it clear that the angle between the force being applied and the lever arm is 90 degrees. And so torque 1 is going to be equal to R1 M1G sine 90 degrees. And torque 2, so this is the torque on the right side, that's going to be equal to R2 M2G sine 90. And one more thing to consider, if we're going to talk about rotation, we're going to have like some way of keeping track of whether rotation is going in a clockwise or a counterclockwise direction. And so by convention, if something goes in a counterclockwise direction, we're going to call it a positive torque. And if something goes in a clockwise direction, we're going to call it a negative torque. And so look at the person on the left. The gravity pulling down is going to want to rotate the teeter-totter in a counterclockwise direction. And so we're just going to call that positive, and we're going to call the other torque negative. And so the net torque in this situation is just going to be torque 1 plus torque 2. And remember, when you have the sine of 90, that is the largest possible number that sine can be. It's 1. And that's another way of saying that all of the force is acting in a direction that supplies rotation. And so that term goes to unity. That term goes to unity. And so you would get R1 M1 G minus R2 M2 G. So here you can see that you're going to have some net rotation of the teeter-totter if this term and this term differ at all. And there's different ways that they can differ. So first of all, you can imagine that one person is a lot more massive than the other. Or you can imagine that if they had the same mass, their leverage could be different. So for instance, imagine they had exactly the same mass, but let's say that the fulcrum was right here. Who would have more leverage? Clearly, the person on the left would have more leverage than the person on the right. And so ultimately, the torque going downward, i.e. rotating the teeter-totter in a counterclockwise fashion, would be greater than the amount of torque rotating in the clockwise manner. So that's kind of a way in which you could think of like having leverage is having more of a lever arm for the same amount of force. But granted, you could go back to a situation where the masses were identical. If the masses were identical and the fulcrum was right at the center, gravity is obviously acting with the same gravitational acceleration in both cases. In fact, you can get rid of those terms. So it's really just looking at the ratios, the proportion of lever arm and mass on one side to the lever arm and mass on the other side. If the masses were completely equal and the lever arms were equal, you're not going to have any rotation. It's just going to sit there. But for the same lever arms, if the masses are all different, you can imagine there's going to be rotation. Or if the masses are identical and the lever arms are different, you can imagine there's going to be rotation. So I want to take this torque idea and link it to angular momentum, just as I took the linear force idea and linked it to momentum. And so remember, let's go back to an object. Let's say that at time 1, it's right here. And then let's say that it's got some radius r from some center axis of rotation. And then let's say that at some later time, also of radius r, that same mass is right here. And in that time, an angle theta has been swept out, meaning that there's this much arc length that's been swept out. And we define that arc length as r theta. Now, previously, I've talked about how that arc length is just length. It happens to be curved, but you could take it and you could stretch it out and figure out how much linear distance is covered for an angle theta that's swept out. And so when you make the conversion that r theta is just linear displacement, then you have these rotational analogs to what we learned about linear motion. And so when we had a linear displacement x, the rotational analog for that is theta. When you have linear velocity v, the rotational analog for that is omega, i.e. the angular velocity. And when you have linear acceleration a, the rotational analog for that is alpha, the angular acceleration. And so I now want to make a case that for linear mass m, the analog for that is what's called the moment of inertia I. And so real quickly, let's say that I had like a box and that box had some mass m. And for simplicity, let's say that I break the mass down into two mini masses. Oh, heck, let's make it 3. Okay. So just imagine that like mass m could also be thought of as these 3 little mini masses, each with mass m over 3. Okay. And let's say that this whole object remains intact and goes with some velocity v in this direction. Well, if it remains intact, it means that all 3 of these mini masses are going to have the same velocity. And so the linear momentum p is equal to mass times velocity. So all of the mini masses that make up the total mass also have the same linear momentum because the object remains intact. Now, if the object flew apart, that's a different story, but imagine the object remains intact. All of the little pieces that make it up are going to move with the same velocity v as the whole object is. But that's not the case when it comes to a mass that's rotating. Now, so this mass right here, imagine if instead the mass was, say, right here with respect to the axis of rotation. So for the same angle theta, can you see before and after there? That's not as much distance that's been covered as been covered out here. And this is the key now. When you think of an object that has some mass and how you can take that mass and break it up into a bunch of mini masses, those mini masses are not going to be covering the same distance for a certain angle theta of rotation. So you have to account for how the mass is distributed across the object. And how the mass is distributed across the object is going to be the moment of inertia I. So just as mass is a linear gauge of inertia, i.e., how much an object at rest wants to remain at rest, and then if you get that object in motion, how much that object resists changing its motion. That's the linear notion of inertia. The rotational moment, the rotational analog for inertia is I. It's an object that is not rotating tends to not be rotating, and once it gets rotating, it tends to resist changing its rotation. So I is the rotational inertia. And so just as like everywhere in the linear equations where you saw x, you can convert it to the rotational equation, put it in theta. Everywhere you saw v, you could put an omega. Everywhere you saw an a, you could put an alpha. I'm going to make a case that everywhere that you see an m, you can now put an I. And by the way, I is going to differ based on different shapes of objects, how the mass is distributed in those objects, and what the axis of rotation is. And so you're going to have to look that up in a table. You'll be provided information about whether it's a sphere or a cylinder and what the axis of rotation is and whether it's a uniform distribution or if the mass, say, is like distributed out towards the periphery. So just as P equals mv, the rotational analog, we're going to say L for angular momentum, and that is going to be equal to I, because I'm going to put an I wherever I see the M. And then you see the V there. Well, I'm going to substitute omega. So that is one way in which you can write angular momentum. Similarly, force equals mass times acceleration. Well, in the rotational sense, torque equals I, where I now is the rotational analog for linear mass. Same concept, inertia. It's just we're dealing with rotation now. And now where I see an A, I can put an alpha. So this also means, right, since force equals the time rate of change of linear momentum, I can also say that the net torque is equal to the time rate of change of the angular momentum. So in both of those cases, if the time rate of change in momentum is 0, that means that there's no net force or no net torque, respectively. So when you have situations where there's no net force or no net torque, you have conservation momentum situations, because if the net force or net torque is 0, and therefore the time rate of change of momentum or angular momentum is 0, no change means constant, which means conserved. So if you have situations where there's no net force, you may want to think about using angular momentum conservation or momentum conservation, where you would immediately know that the total momentum of the system before and after is the same. So one last thing. So going back to, say, a teeter-totter, and let's say we've got some mass M on the end. And let's just say someone came along and was going to push them upward. So we can also think about the angular momentum here, where the angular momentum, just like when we did the force, we thought of how you had a force and you had a lever arm, and you had to think about the direction of the force that was acting in the direction that would actually cause rotation. So if you have some velocity v and you're moving in a circle, so you sweep out some angle theta, and so you're going at some arc. So if you're moving in circular motion, when you look at a given moment in time, the velocity that you're traveling in is going to be perpendicular to the lever arm. In other words, it's going to be tangent to the circle. And so angular momentum, L, which I showed you can be expressed as I times omega, can also be expressed as the cross product of the lever arm, R, times the linear momentum, V. But again, you are not required to know how to do a cross product. And so similar to how I showed you another way in which you could think of when you're talking about torque, which is the force vector cross product with the lever arm, similarly, you can think about the cross product of the lever arm and the linear momentum as being equal to the magnitude of the lever arm, the magnitude of the linear momentum, and the sine of the angle between them. But here's the thing, the linear momentum, i.e. mv, that's always going to be tangent to the circle. And so if you're tangent to the circle, that means that, so for instance, the lever arm here would be R. Well, that's always going to be 90 degrees. If your linear momentum is always tangent to the circle, then a tangent is always going to be perpendicular to a lever arm. And so this is going to be 1, because sine of 90 is equal to 1. And again, that's because the linear momentum, mv, is always going to be tangent to circular trajectory, and the lever arm is always going to be perpendicular to the tangent. And so to complete this, if I'm talking about just the magnitudes now, it's just mass times whatever the linear velocity is times whatever the lever arm is. And so when you think about angular momentum, you have to think about the mass and the velocity, but now you also need to think about what is the distance of the object from the axis of rotation. If r is smaller, you're going to have less angular momentum for the same amount of mass. And that's the whole reason why you can't just use the linear mass m in the rotational notion of inertia, because for a given mass m, if it's at different distances away from an axis of rotation, then it's going to cover different amounts of distance for the same angle being swept, which means that its linear velocity for the same angle being swept is going to differ. So one last time, going back to the linear case where you can think of a mass being broken down into smaller bits. If that mass stays intact, its linear velocity for all its smaller bits are the same. But if you think about the rotational sense, then if you think of an object being thought of as a bunch of smaller bits, and that object is rotating, the smaller bits that are closer to the axis of rotation are not going to have as much angular momentum as the bits that are further away. And that's why when you think about moment of inertia, you have to think about how the mass is distributed in an object. And that includes how much mass and how far away it is from the axis of rotation, but then it also is what the shape of the object is itself, and in what orientation is that object rotating vis-a-vis the axis of rotation. And so I encourage you to continue to understand that many of these ideas are built off of previous ideas. We've seen how our understanding of linear motion really allows us to build our concepts of rotational motion. And similarly, like our notions of linear force and linear momentum allow us to build our conceptions of torque and of angular momentum.